In this video, we're going to be looking at topic 1G, covalent bonding, and we're going to be focusing on these single science outcomes as part of the IGCSE chemistry course from Edexcel. So what do we have to know for this topic? Well, we need to know what we mean by a covalent bond and how that is formed. We then need to know the different structures that we can get in a covalent bond and then how they relate to specific properties, in particular melting and boiling points. So what do we mean by a covalent bond? Well, in a covalent bond, we're getting a pair of electrons being shared between two non-metal atoms. So this is different to what we saw with ionic. For ionic, we saw a transfer of electrons, and we saw that between a metal and a non-metal. For covalent, we are now only focusing on non-metals, and rather than giving away their electrons or receiving an electron, the two things share them together. And when this happens, we get the electrons being held in the centre, and we get a strong electrostatic attraction between the positive nuclei, or the nucleus of each of the atoms, and then that shared pair of electrons. So the electrons sit in the centre of the two nuclei, and that attraction is what holds them together. And we can see that in this diagram here. Now, how does this sharing actually happen? Well, what we get is we get an overlap of our electron shells. Now, at single science, you are not required to do dot and cross diagrams. They are double only. But it is important for you to see how this actually happens. So if we take one atom and we have our nucleus in the centre, it is going to have an electron. Yes, we're going to say that this is a hydrogen atom. So it's got one electron. And what this does to bond with another another non-metal to form a covalent bond is they overlap their electron orbitals like that. And then this one also has an electron. So now you can see that we have that shared pair of electrons sitting in this overlap, and we have the nucleus on either side from each of the two atoms, and it's this attraction for the electrons to the nucleus that holds the covalent substance together, and that is a covalent bond. And you sometimes draw it like just a line to say that that's the representation of the covalent bond. Now, the reason that they do this is because, with a couple of exceptions that we don't need to really know anything about, but the majority of atoms want to have 8 electrons in their outer shell. And this is known as the octet rule. And the reason that they want 8 in their outer shell is because that means that they will have a full outer shell, very much like the noble gases. And that's why the noble gases are unreactive, because they have this full outer shell. They cannot form a bond with anything else. So what our substances will do is they will have the nucleus in the centre, and they will then, let's say we have 4 electrons, they are going to then share with 4 other substances, which are the dots, to make 4 covalent bonds, and that then gives them that full outer shell. So by sharing the electrons with something else, they go up to that total of 8 electrons, meaning that they are now stable and they have that full outer shell. So this, as we said, is known as the octet rule. Now, there are a certain set of elements that you have to be aware of that follow this octet rule, and they exist as what we call diatomic molecules. And this simply means 2 atoms. So the di meaning 2, atomic meaning atom. And these are 2 atoms that are covalently bonded together. And there are 7 elements on the periodic table that exist like this. You will not find these 7 elements as one atom on their own. They always exist as a pair. And the 7 elements are hydrogen, which is in group 1, so it has that one outer electron, like we can see in the diagram. Nitrogen, which is in group 5, and that forms what is known as a triple bond, which means that we share 3 pairs of electrons. And we get something like this. Fluorine, iodine, chlorine, and bromine are all in group 7, so they all have 7 outer electrons. Now remember, you're not expected to draw this for single science, it's just to make you aware. So we're going to have our chlorine, and then it bonds with another chlorine that also has 7 electrons, and that overlap is the sharing electrons, giving each 8. So all of our group 7 substances will bond like that. And then oxygen is in group 6, and it forms what we call a double bond. And that simply means it shares 2 pairs of electrons. So we get an O with a double bond like that. So our single bonds between hydrogen, fluorine, iodine, chlorine, and bromine, a double bond with oxygen, and a triple bond with nitrogen, and these are our 7 diatomic molecules. As I said, you're not expected to draw a dot and cross diagram. It's just important that you do know these, because these can come up when we draw or we write equations, and you have to know that these are 2 atoms bonded together. So now we're going to move on to talk about the different types of structures that we can have. So we've just learned that a covalent bond is a shared pair of electrons between our 2 non-metal atoms. Now, that's great for one covalent bond, but most of our substances in the world that are covalently bonded will contain more than one. And that then leads on to how these are put together. And we have 2 different types of structure. We have giant structures and molecular structures. So giant structures are ones that have no fixed number of atoms. So an example would be silicon dioxide, or SiO2. And similar to our ionic substances, what this means, or this formula, is it's simply the ratio of the atoms. Meaning for every 1 silicon atom I have in my structure, I have 2 oxygens. But it is not fixed that every sample of silicon dioxide has 100 atoms or 200 atoms. They can vary, and they form this giant lattice structure, which we'll talk a little bit more about later on. We also have a molecular structure, which means that we have a fixed number of atoms. For example, water, being H2O, every single molecule of water will have 2 hydrogens and 1 oxygen. That doesn't change. That is a fixed number. And it is this small molecule that forms the structure, and we call these molecular structures. So another example of a covalent molecular, as I said, could be water. We can also have ammonia, which is NH3, methane, which is CH4, or carbon dioxide. These are all molecular structures, being CO2, because they all have that fixed number of atoms. So we have, for example, in carbon dioxide, 1 carbon to 2 oxygens, and we always have that. So some other examples could be substances called fullerenes or diatomic molecules. So fullerenes are what are known as an allotrope of carbon, and all we need to know at the moment is an allotrope just means a different type of carbon. So carbon is not just 1 single carbon atom. Okay, it can bond together with 60 or 70 carbons, and they form the shape of a football, like we can see in the diagram here. And these are covalent molecular substances. Okay, we don't need to know too much about fullerenes, just simply that they exist. The other type that we could have, and this is just one of many different examples, are the diatomic elements, which are ones that we just met. So those are those 7 elements that exist as 2 atoms covalently bonded at room temperature. But the most important thing is that they are fixed with those 2 atoms. That's not something that we can change. So that tells us that these have to be molecular substances. Another thing that we must be aware of in our covalent molecular substances are the types of bonds. So in between the atoms themselves, they are bonded by these strong covalent bonds. So we have our water like that, and that means that that line showing that this is your strong covalent bond. When you take a sample of a substance that is bonded with covalent molecular structures, what we need to understand is it's not just one atom or one molecule on its own. We actually have lots and lots of these water molecules in a specific sample. And there are bonds in between the molecules that hold it together. And this is going to link into the movement between solids, liquids, and gases, which we will look at in more detail later on in the video. So in between all of our water molecules, there are forces known as intermolecular bonds. And that simply means that they are between the molecules. And these are very, very important, as these are what keep the covalent molecular substance together. So the strong covalent bonds join the hydrogens and oxygens, but the intermolecular bonds, very importantly, are weaker. And this is something that we take advantage of with our melting and our boiling point. Moving over to giant covalent networks, an excellent example is, again, carbon. So we've seen that carbon can be a fullerene, which is that molecular substance, but it can also exist as this giant covalent network. And carbon will exist in two forms like this. It will exist as diamond and as graphite. So they are both made up of carbon, they are just bonded differently. And this difference in bonding gives them very different properties. So in diamond, each of the carbon atoms forms 4 covalent bonds with other carbon atoms. So we have our 4 outer electrons in carbon, like that, and each of those outer electrons forms a bond with another carbon, which then forms bonds with another one, and so on and so on. And we start to get this giant 3D structure being formed, and that's what this is here. And we call this a giant lattice. Okay, and we've seen that word before when we've been looking at ionic substances. So we have that lattice structure. Graphite, on the other hand, is slightly different. Graphite only forms 3 covalent bonds with another carbon. So we've got, again, carbon normally has 4 outer electrons. 3 of these are involved in bonding, so that causes that 1 outer electron here to become what we call delocalized. And that is just a fancy way for saying it becomes free to move. And the way that this works is we get a giant network of our carbon atoms with 3 bonds forming a layer, and then we form other layers underneath. So we get this sort of layered structure of hexagonal plates. And these are held together with these intermolecular forces, which is what are the dotted lines. But in between the layers, we then have these delocalized electrons that have come from all of those carbon bonds. And that is what allows graphite to conduct electricity. Now, we don't need to go into too much detail about that. We just simply need to know that graphite forms 3 bonds with 3 other carbons, and it is a giant covalent structure. We can also find it in boron and silicon compounds. These are less likely asked about, sometimes asked about silicon dioxide, but very rarely the boron. And we said previously that silicon dioxide has that structure of SiO2. And please remember that that is the ratio. So all of our covalent networks, their formulas show the ratio of the atoms, not the actual number. Whereas for our molecular, the formulas show the actual number because they are fixed. So this now leads us on to the last part of this topic, which is looking at the properties. And the main property that we have to look at in single science is melting and boiling point. So if we have a covalent molecular substance, they have got very low melting and boiling points. And perfect examples are things like ammonia, which is a gas at room temperature, or water, which boils at 100 degrees. Those are quite low melting and boiling points. And the reason for this is we are not breaking the strong covalent bonds here. The strong covalent bonds in a molecular substance are not broken when we're trying to go from a solid to a liquid to a gas. What we are actually breaking are the weak intermolecular bonds. And because these are weaker, they require less energy, which gives us a low melting point or boiling point. So if we have to break weak bonds, we need less energy, giving us this lower value. And the opposite to this, when we have a giant covalent substance, these have very high melting and boiling points. And the reason for this is that this time, it's not the intermolecular bonds, we are actually breaking the strong covalent bonds. So these need a high amount of energy, giving you your high melting and boiling points. So the melting and boiling points are all to do with how much energy you need to break the bonds. For molecular substances, it's the weak intermolecular bonds, so that's a low boiling and melting point. Whereas for giant substances, it's the strong covalent bonds, therefore we need high energy, giving us our high melting and boiling point. Now we should be able to put everything that we've learned in this topic into past paper questions. So hydrogen chloride is formed in the reaction between hydrogen and chlorine, and we're given the equation here. So H2 plus Cl2 gives us 2HCl. Note these are our diatomic elements joining together. And each molecule in this equation contains the same type of bonding. We want to name it. Well, this whole topic has been about covalent bonding, so that of course has to be the answer. But in an exam, how would you know? Well, it's the fact that these are two non-metal substances. And because they are two non-metals, that means that we have covalent. For part B, the bonding in a hydrogen molecule is strong, but the boiling point of hydrogen is low. We want to explain why. So this is where we have to think about what bonds are being broken. So we are breaking weak intermolecular forces and hydrogen. And that requires a low amount of energy, which therefore means that we have a low boiling point. Please note that you cannot use the word less here. You can't say less amount of energy because you're not comparing it to something else. So you have to just use the word low or high if it's high energy. Because we're not comparing to anything, we cannot use less or higher. And then for part C, explain how the two atoms in a chlorine molecule are held together. Well, that's all of this electrostatic attraction. This is our key terms that we use. And this is between the shared pair of electrons and the positive nuclei. And you could even draw a diagram if you wish. You could show that you have this overlap with our positive nucleus and our shared pair of electrons. But it's that electrostatic attraction that holds the atom together. And then lastly, when water is added to a mixture of sand and cement, we get a reaction taking place between the silicon dioxide and the calcium oxide, and we form this salt. We're not really worried about the salt at this point. What we want to focus on is, in terms of its bonding and structure, explain why silicon dioxide has a very high melting point. And this is for 4 marks. So this is a very good question in the fact that you have to talk about the different types of bonding, the different types of structure, and then what effect that has. So first of all, it contains Covalent bonding. We know this because it is two nonmetals joined together, silicon and oxygen. It has a giant lattice structure, because we said that silicon is one of the ones that will always form this giant network structure. Then we have to think about the high melting point. Well, what could be causing that? What bonds are we breaking? Well, we are breaking very strong covalent bonds. And then what effect does this have? Well, they require high amounts of energy to break. So we're just breaking it down step by step in the question. So in terms of its bonding and structure, well, we say what is the bonding, what is the structure? And then thinking about what bonds are breaking and why that has an effect on the high melting or boiling point. And that gets you your 4 marks. So there's the mark scheme for those questions if you have been trying them yourself at home. That's everything for topic 1G, covalent bonding, for the single science course. If you have any questions, feel free to leave a comment below, and we hope to see you back soon.